Hi there. Today we'll be diving deep into the internals of how Nginx works. If you have been living under the rock and you don't know what Nginx is, it is basically a web server, an open source web server, mind you, which was brought to inception in 2004, and now it powers 33.8% of the web servers in whole of the World Wide Web, www, right? So you can see that it is quite prevalent out there, and the technology and the software engineering that has been done in order to bring it to fruition is a marvel in and of itself. So what earlier used to happen was there was a problem with how to manage the C10K problem. What is this? How did we come to this solution? Let's again start right ahead with now. Okay, so yeah, Nginx architecture. So at the time, there are two types of web servers, mainly two families of web servers. One is the thread-based web server, and the other is the event-based. Event-based. In thread-based, what usually happens is for each connection that a client requests, the web server spawns a new thread, either a new thread or a new process, and that process or a thread is responsible for handling that connection. Well, some of the common examples for these are Apache servers and Go servers as well. On the other hand, we have event-based servers. What event-based servers do is there is only a single threaded process. There is only a single thread which handles some multiple simultaneous connections of itself with non-blocking IO. So there is no blocking involved, and one of the common things, as we will discuss now, is Nginx as well as Node.js architecture, which by default you must have used it if you are a new software engineer and you have just started dabbling your foot into the software engineering web development world. So that is what I have written here as well. So the thread based, again to recapitulate, thread based is basically one thread or process per any client connection, and in event based scenario we have one thread managing thousands of simultaneous connections. So of course there are some benefits, there are some drawbacks to each of them. In thread based, the obvious benefit is that the entirety of the software is quite simple and intuitive to follow. Whenever a new client comes in, okay, you fork yourself and create a new process, and that process will take care of handling. So from a software point of view, this was quite simple to do. In event based, but the other drawback is, now you can imagine that as you have more number of clients coming up, you spin up more number of processes, which each process is a very heavyweight thing from the OS itself. Right, so there is a huge memory footprint ultimately. If you have 1000 connections, and even if you allot 1 megabytes to each of the connection, then you would have ultimately 1 gigabytes of additional memory. So you can see the problem right there, right? In event based, what happens is you have a certain set of processes, and each process is a single thread itself, and that single thread is responsible for handling all of the connections, all of the simultaneous connections. How does Nginx do it, or more particularly how does even Node.js do it, is they are quite similar. They fall into the same family of the web servers, so we will discuss about it. So first, a brief about Nginx. It was, as usual, as I told you about, it was published in 2004, and it is an open source event based web server. This is one of the core things that you need to focus on, is that it is event based web server. Whenever an event comes in, hey, you got something, then it begins processing that, or it runs in a loop and picks up the event as they come. So it is a web server, but it also contains additional functionalities such as caching, access and bandwidth control. It also acts as a reverse proxy or as a load balancer. So Nginx was created to solve the C10K problem. What is the C10K problem, you might ask? Well, earlier back in the day, there was a problem that if you had 10,000 simultaneous connections, how can we ensure that the web server is able to handle all of these simultaneous connection requests without crashing down and without too large of a memory footprint? You wouldn't want your web server to consume about 10 gigs of RAM, right? That would be far too costly for you, because there are other services running as well on the web server nowadays than it was before. Back in the days, of course, their web servers were a single machine, and that only a single Apache web server was running, so that made sense now. But given the proliferation of web servers that we have today, it is not the only process, and of course the memory footprint being high would be detrimental to the web servers that we have. So the C10K problem was there, the handling of 10,000 simultaneous connections, and Nginx was created in order to mitigate, in order to solve that, so that we have high concurrency, with a higher throughput and less memory footprint. So Nginx is more suitable for non-linear scalability. As I said, as you have the increase in number of simultaneous connections, if more number of clients try to access the web server simultaneously, the web server should be able to handle all of them pretty relatively easy, and the growth should be non-linear. It should not grow as per the request, right? And increasing request per second, same, you have the throughput here, and you need to also keep these factors in mind. So what is the goal for designing Nginx? As I told you before, it was designed to handle high concurrency with high performance and efficiency, that is less footprint on system resources, be it memory or IO or blocking operations, or even introducing latency. You don't want, as the number of services, as the number of client connections come up, you don't want the latency to go up as well, right? So this was the goal, and Nginx was designed with this architecture, designed with this goal being kept in mind. Yeah. So let's dive into the nitty-gritty details and let's see the architecture that we have. So what does Nginx do? Whenever you instantiate Nginx, a master process is created, and that master process is responsible for reading the configurations, and then based on the configurations that you have specified, it creates some other processes. It forks itself and creates other processes as well. So there are many worker processes that you can see, and there are as well some other processes like a cache manager and a cache loader. What these are, we'll get back right into it in greater detail in the next section of this video. So these are the worker processes. So master process first runs, it sets up the basic infrastructure that is required, and then it forks itself and creates some child processes. Many are workers, and there are 2 additional cache loaders and cache manager. So each spawn process, one thing to note is that each spawn process is only single threaded. There are no multi-threads involved so far. I'm not sure about the so far part, but the documentation which I used, it is a single threaded, right? And how many number of workers can you spawn? Well, the master process, if you have set it as an auto mode, worker process auto, then the number of workers is dependent on the number of hardware threads that you have. If you have 4 cores and it has been configured to use 2 hardware threads per core, then you will have 8 number of workers eventually. So why this was brought into the play was, the main thing was to have Nginx run almost always on the CPU. If you're a computer science graduate, or even if you know a bit about how operating systems work, the CPU preempts many of the processes continuously. So if there is a blocking call, the CPU, the OS, would preempt this particular blocked process, and then there will be additional time delay introduced. So we would want to avoid this scenario. We would want our processes to always be present in the CPU. So if we have multiple cores, what better solution than to glue a single process to each of the cores that we have? That way, it is guaranteed, it is almost improbable that at any instant point of time, all the processes get preempted from the CPU. Even if 1 or 2 goes away, then there would be n-1, n-2 processes still having the Nginx web server running on them. That is why we would almost always be on the CPU all the time. So this was the reasoning behind why the number of workers is by default set as the number of hardware threads. I hope you got that point. So yeah, each worker process handles multiple connections in a non-blocking fashion. This is quite crucial, because if you get blocked, if you remember your computer science classes, if you get blocked, then CPU would preempt your process and it will be put into the waiting queue. It will wait for the event to happen, and once it gets the event, it will be put in the ready queue, and then the CPU would ultimately, the scheduler would ultimately pick it up. But there is a very big delay being added here. So we want to avoid that, and we want to reduce the number of context switches as well, because they add unnecessary overhead to our processing. Remember what our goal is, that we want the web server to be scalable, to be able to handle multiple simultaneous requests with a high throughput, low latency, and low memory footprints. Yeah. And how does Nginx achieve this? Well, the main crux is the event notification mechanisms that it improves, that it uses in order to get this. So there are some syscalls, KQ and epoll, which is heavily used in the Nginx architecture. So now let's try to cover what processes do we have. We have the master process, we have the cache manager, cache loader, and the workers. What do these signify? Let's just find out. So first of all, let's start with the master process. The master process, as you quite remember, is the first process that is run when you instantiate the Nginx web server. The master process is responsible for reading and validating the configurations, where you will specify how the web server is to run, what are the number of workers that it should spawn, etc. Then it also creates, binds, and closes the sockets. Basically what happens is, whenever we instantiate the master process creates a socket and it binds it to a port, let's say 8080. So this socket is now bound to port 8080, and the master assigns this as a listener tag, right? So this port is now listenable, and now it will spawn other child processes which will inherit this socket, and now they will be reading the connections from this socket, they will be listening to this socket. Yeah, so reading and validating configurations is one of the aspects, creating, binding, and closing the sockets. It also maintains the starting, termination, and maintenance of the number of worker processes that it would use. It also is responsible for reconfiguring and any upgrades that happen without incurring any downtime. How does this happen? Is, again, this is a very beautiful solution from a software point of view. So we have the master and we have some workers already running. Now if the user makes some configuration changes and it asks it to reload, how to ensure that there is no downtime? The server does not actually go down and instead keeps running, but the new configuration is applied gradually. So here what they do is, we have the workers already running. So the master process creates additional child workers, additional worker processes based on the new configuration. So we have the new ones created over here, but it does not terminate the already existing worker processes by itself. What actually happens is the master spawns new processes, new child processes, worker processes based on the configuration, and then it signals the previous workers to gracefully exit. What they do is they complete any connections, they complete any open connections that are presently there, and once they are done, they shut themselves down and do not read any new connections afterwards. So as you can see, update configuration on disk, SIGHUB signal is being sent to the master when you run the command, and then it spawns the new workers. Based on the new configurations. Nginx keeps on running, but the old workers processes complete their pending task, and at the same time they did not take in any new task, and then they gracefully exit. So this is how you maintain 100% availability even if there are configuration changes. What if in case of an upgrade to the server as a whole, as a binary upgrade? What actually happens is, the original master process was there. We spin up a new master process with new worker threads, and now it has access to this, and it now listens to the original socket. The old master and the workers stop listening to the socket, the listening socket, and instead they try to complete whatever processes, whatever connections they have already taken up, and once those are done, it is terminated. So this is again an example of graceful termination. And then quit the old master process and it will terminate gracefully, and now we have the new upgraded version running without incurring any downtime. So what we have achieved is the holy grail of having zero downtime for an upgrade, right? So now let's get into the meaty stuff where the most of the work happens. As you recall, we have the master process, and most of the actual web server-y stuff is done by the worker processes. Now we will get into the nitty-gritty details of how they work. So before beginning to expound upon how the worker processes function, it is imperative for you to know how an HTTP call is being made through the client. So whenever a client, let's say we have a client here, whenever a client initiates a new connection, it is the kernel that takes responsibility of establishing that connection. That is, we do a TCP handshake, and that is done via the kernel itself. The kernel has two queues, basically. It has two queues to maintain the connection list. One is the SYN queue, which contains connections that are still open, that have not been acknowledged, and whenever a new connection is trying to be established, it is put into the SYN queue. The kernel then responds back with a SYN ACK, and the client then responds back with an acknowledgement. And when this has been done, this connection is now moved to the accept queue. Now we have moved it into the accept queue, right? So this is how the initial connection establishment is occurring. Then after we have the accept, we have the connection and the accept queue, this is now made available. Cool. So now this is made available because of the socket that we were listening to. Now the kernel decides which of these worker processes will get to accept this connection. So it sends the notification to any particular worker. Again, the load balancing in here is taken by the kernel itself. The worker then accepts this connection, creates a socket for it, and registers with the kernel that, hey, for this socket, if any event comes, send it to me. I am interested. So it registers its intent, its interest in that particular socket. It creates a data structure as well in its memory, so that whenever the new data comes in, it would be able to access the particular resource in O of one time. Again, these details are explained further. I have included some sequence diagrams to explain the process. Right. So once that is done, we now have the data. We will get the internet request, and you can see there are multiple components here. So basically what everything happens is, every connection that we have is a state machine in and of itself. Now we have the loop, right? I didn't even talk about the loop so far. But what actually happens is that we have an event loop going on within each of these processes. So each of the worker processes. So what ultimately happens is, it goes in a loop. It always checks, okay, do I have any new notifications? If not, then do I have something else to work on? It does that, and if there is any IO call to be made, it makes a non-blocking IO call, and it goes ahead and picks up a new thing to work on, and it waits until that IO call is complete, and then it gets the notification, and then it completes the work that it was doing, picks up the new notification, and processes it further. So based on the events that it receives, it updates the state. That is why any connection could be termed as a state machine that we have. So every request is a state machine. It stores the state. Basically, it does not store the state. It depending on the event that actually occurs. It just invokes the next state handler, invokes the next event handler to say. So that is how the event loop comes into picture, and this is mainly responsible for how the memory footprint is kept low while still ensuring that we have multiple connections simultaneously in place. So we have the internet request coming up, and there are many modules which actually take care of the different steps, different steps of processing the request that is coming. Basically, if you have to read and parse the incoming request, you have to perform you have to perform network address translation on it, you have to spoof the ID, etc. So for all of these tasks, there is a specific module available as well. So it is basically a configuration. It is basically an orchestration of different modules which work together to process a single request. It depends on the generated content, and then that could also maybe call upstream services to get further data, to make further calls, and then it creates the response filters, it logs it in, and it reads the request headers, substitutes it with network address translation stuff, and then sends back the result. So all in all, the crucial thing to note here is that there is an event loop, and all the syscalls that are being made here are non-blocking in nature. That is why, one, there is no preemption involved, so the context switching is kept to a minimum. Of course, that would still happen if the cache memory becomes full, if there are no connections. If we run out of resources, then of course the process would be blocked. But other than that, in normal scenarios, what happens is that whenever an IO call is required, or whenever you have to read from a socket, all of these are non-blocking in nature. So once you say, okay, I want this, now when this done, notify me. Till then, I'll be busy doing other stuff as well. So this is the crux of how Nginx is able to handle multitudes, is able to handle each of the worker process, is able to handle thousands of connections on its own. Now let's dive into the sequence diagram about what I explained to you earlier. So how the connection acceptance and registration is being done. So you are a client, okay? You make a call to send act, but before that, let's focus on the initialization. So when you start up the Nginx server, a master process is booted up. Master process creates a socket, it binds it to a port, and also adds in a tag for listening to it. It also sets some socket options, and it forks itself to create the other worker processes as well as the cache manager and the cache loader, which we'll discuss. So now these worker processes now register their interest for any events for listening on the port, for for listening on this particular socket. Hey, if anything comes, please inform me. Cool. So now, whenever a new connection comes in, as I said before, kernel takes care of doing the TCP handshake, and once that is done, the connection is placed in the accept queue, from where now it is an accept queue. So it is now readable. This event is now emitted, and the event loop picks up this event, processes it. So if this is a new connection, then it sends an accept. What it does is dequeues. It dequeues the connection that was placed in the accept queue, and it returns the new socket file descriptor for it. Now, how does the worker process know how does the worker process know to monitor the state of a particular connection when it deals with multitudes, with hundreds of thousands of, not hundreds of thousands, but thousands of connections, simultaneous connections, is that it creates a structure in its memory. It creates a connection structure for each of the new socket. It also includes the process. It also includes the connection state, which next event handler it should execute and stuff. So it creates a new connection structure, sets it to non-blocking mode, and then it registers its interest. Ki, hey, for this particular connection socket, if any new event comes, just notify me. And it returns back to the event loop and tries processing other events that it could find. So this is the whole flow of how connection is being accepted and how the worker processors register their interest in handling the particular connections, right? So now the other one is a bit of a overall overview of how the entire thing works. So now that we have accepted a client connection, now the client sends an HTTP request to the kernel. The kernel now will try to notify the web worker that actually had registered their interest into listening to it. So now the notification is sent to the event loop of that particular worker process. It is a readable notification. The event loop completes this task which it was doing, then it takes it the event, processes it, and now it tries to get the request to read. Now there are multiple handlers for it. Now it read key, okay, what are the headers for it? Let's just find the headers, and that we will decide what next steps should be. So it gets the connection from the event data, calls the read handler. So there is handler. So whenever an event occurs, the worker processes trigger a handler function in order to handle that event, as the name suggests. If you have come from a JavaScript background and you're familiar with asynchronous programming, then this would make much more sense to you. Okay, so we have the read socket data, it returns the request, it creates the HTTP request structure, sets new read handler. So whenever a particular thing is complete, it now sets the next stage that should be executed for it, and now it goes back to the event loop. Now it does something else, and once it gets back to this, it creates an event, then it calls another handler which we had set before, and this way further processing is done until and unless we get back to the right response data, and the kernel then sends it back to the client. So what a fascinating solution. What a fascinating solution to this. Now, because of this solution, Nginx is able to keep its memory footprint low, because even if you use multiple workers, even if you use a single worker, and for each connection you do create a data structure in memory that is significantly lower. The cost is significantly lower than spawning a new thread or a new process entirely on its own to just handle that new connection. So this is basically the architecture. This is the flow of how Nginx is able to act as a very available, as a very high performant. It's quite a high performant web server that is now used everywhere. So I hope you liked this video. I hope you were able to understand, and maybe you would also like to dig deep into how Nginx actually works in further detail. I will also include resources down in the description somewhere down below, so that you could also pick up and read many things on this. So yeah, that's it for this session, guys. I will see you in the next one. Thank you.